Now the solid rocket boosters were only used at very low altitudes. At low altitudes you have a lot of atmospheric pressure. The more atmospheric pressure you have, the smaller these rocket nozzles will be. Why is the rocket nozzle smaller? Well, because in a very high altitude, like the near vacuum of space, then you already have plenty of pressure. If you don't have enough pressure, then all the gas will be sucked out, and then you have no thrust. So if I want to simulate this, I can say we would have to first talk about the area of such a spacecraft. This nozzle here, this nozzle shape is the area, and at ground level that's extremely low. So then what will happen is, as the spacecraft typically ascends, at separation, which is about t plus 2 seconds, 2 minutes, these boosters will separate from the main shuttle pod, the main shuttle aircraft. After this happens, there will be smaller thrusters, which are made out of ammonium, on the solid rocket boosters, and then these will be used to guide these solid rocket boosters away from the main station. If I wanted to show that. This is going to be the point of separation, and this will be the point of circularization. For context, the space shuttle is basically lifted off onto the launch platform like a giant payload. It's first assembled vertically, and then it's converted to the horizontal position in order to refuel it. Once the solid rocket boosters are fueled, we can take it to Kennedy Space Center. These are usually contract workers, and once the contract is finished constructing these solid rocket boosters, they're taken to Kennedy Space Center, assembled into the NASA space shuttle, and then they're taken to the launch pad, which can take several months. That's how heavy it is. Once this is assembled, you would take the space shuttle to the launch pad, and then this orange tank will be fueled with hydrogen and oxidizer. The hydrogen and oxidizer is used to power. The hydrogen and oxygen will be used to power the main shuttle engine, which you can see. These are the main shuttle engines. They use hydrogen, oxygen, and the RCS thrusters that you can see on the other side of the spacecraft. They use monomethyl hydrazine, which is it's a small monomer propellant, but it's not very big. At about 2 minutes, all of this will be completely abandoned. The only thing that will be heading into near Earth orbit will be the space shuttle and the external fuel tank. There will be no more solid fuel left. The only thing that will be left is hydrogen and oxidizer.
Is the standard thing for the whole shuttle, or it depends on the speed?
No, they'll use the same speed. So, for example, if a shuttle was taken, the shuttle will take off in 2 spaces. Firstly, Kennedy Space Center, another space center in California. Depending on the day and the weather, it will take about 2 minutes. But if it got too late, it will be taking about 2 minutes and 30 seconds.
No, I don't know whether it depends on the speed, vertical speed, or
the speed will be the same for every spacecraft, but the vertical speed is constant for the entire thing. So once we can separate that, it's completely abandoned, and it reaches a height of about 200 kilometers for this hypothetical flight. This is known as the apogee. The apogee is a part of your orbit. It's the highest part of your orbit, essentially. It's the highest point that your spacecraft will ever reach throughout its entire lifetime, and the periaxis, or the perigee, is the lowest point that it will ever reach. We can calculate that in one way. This is a basic model of the Earth and our orbit. This is R1. This is R2. R2 is the perigee, and R1 is the apogee. Now, something that's very important is the semi-major axis. The semi-major axis is a combination of R1 and R2 in order to create an average of both. That's why it's marked as A. So this would be going to be the A. Now, it's important because we use it to calculate the speed of the space shuttle at any given time. If the space shuttle reaches 200 kilometers, the speed that it will require to maintain that orbit is obviously different from the speed that we would need to maintain an orbit of 300 kilometers, or 400 kilometers, or 500 kilometers. And it's also dependent on the mass of the object that it's orbiting, because every single thing is mass, and every single thing has its gravitational attracted to each other. This pen is gravitationally attracted to the Earth, and so is the space shuttle. So we will calculate that as such. Times m. G is the gravitational constant, which is 6.67 times 10 to the negative 11. This is extremely important because we're using it to calculate the standard gravitational parameter. The standard gravitational parameter is how much an orbiting object, like the space shuttle, we pull towards the Earth or the ground. So, this is the mass of the Earth, and once we combine this with the mass, with the gravitational constant, we get the standard gravitational parameter, which is typically written as this mu. Mu is the amount that we use for any given planet. If we wanted to calculate an orbit around Jupiter, for example, Mars, our lovely friend, the Moon, or anything else, we would use the mu of that particular object, or the standard gravitational parameter. So, if we want to calculate, for example, this is the basic equation that we would use for that. R is the current altitude that we would use, and R1 and R+2 are the apogee and periapsis. So, for example, let's say we have an orbit like this. This is our apopsis, it's 400 kilometers. This is our periapsis. It's 200 kilometers. We calculate this as such. And then we use those plug into this equation here, which is our current position. If our current position was 300 kilometers above the Earth's surface, and the space shuttle was, say, flying in a very stable orbit, or an elliptical orbit, as this is an elliptical orbit, then we would replace R with 300 kilometers. Anyway, once we reach apogee, which is here, and in terms of the space shuttle, that's about 200 to 300 kilometers, depending on the mission. The space shuttle has gone as high as 500 kilometers before, but 300 to 200 is generally a baseline. We would gimbal the engines, and then we would reach something known as the main engine cutoff. The main engine cutoff stage is the point of the flight where the engine is completely cut off, and the fuel is left about 5 to 10%. We don't cut off the engines fully at, say, when the fuel is completely depleted, because that can damage the engine. Even in a standard aircraft with jet engines, if you let the fuel starve it, then the engine will be permanently damaged. And because the space shuttle must be reused, it's typically about 10%. At apogee and main engine cutoff, which is main, it's MEC, the external fuel tank, which is this fuel tank, is completely disconnected from the aircraft. And there are two horizontal flaps underneath the aircraft, which is which is where the heat shield is. And these valves are responsible for bringing hydrogen and oxidizer into the main engines. You can see it here. This is the external tank. It carries liquid hydrogen, liquid oxygen, and these flaps, these straps essentially, are responsible for bringing it into the aircraft. After the external tank is completely detached, only hydrogen and oxygen used on board is used for life support, not fuel, but life support. The reason for this is the remaining engines that are used for orbital maneuvers, which is the only thing the shuttle will be doing after this flight, aren't used for anything else except, well, they use monomethyl hydrazine, which is a monopropellant, and I'll get into that later. But now I'm not showing the picture. These fuel cells carry hydrogen and oxygen, and they are sent into a fuel converter, which converts this hydrogen and oxygen into water, where it also converts it into coolant from the water. And once we can create such a thing, it's very easy. Some of the oxygen is also used for breathing space for the astronauts. If the oxidizer runs out, then we'll have an asphyxiating crew. That's going to be quite bad. This is the flight deck. The flight deck is responsible for controlling all parts of the spacecraft. Until apogee, or until main engine cutoff, mission control will essentially control most of the flight. The astronauts will not make much manual corrections, apart from maybe a few standard procedures, such as leveling off the engines to about 80% until main engine cutoff. But apart from that, mission control will do most of the heavy lifting, which is why the spacecraft is so powerful. Here you can see the engines that I was talking about. These are the engines that run on liquid hydrogen and oxygen. These are the engines that carry until main engine cutoff. And if one of these engines fails, the spacecraft can still fly, because it's designed to fly with two engines, but it will just take longer, and perhaps the mission will be much more expensive. But it's still survivable. If it loses more than two engines, then it will have to perform an emergency landing, which is indeed possible, but it just means that the periapsis after apogee will be much less, and it'll be a successful failure. This is the payload that the space shuttle generally carries. It can carry all sorts of payloads. When it was constructing the space station, it carried several compartments, modules. It even contracts to Russia, and several Russian modules were also brought up upon the space station. The latest and probably one of the most popular flights, famous flights, was when it took the Canadarm. The Canadarm was a contribution by the Canadian government to NASA's space program. They essentially constructed a robotic arm that would allow the astronauts to connect parts of the ISS together without directly going on a spacewalk and interfering with the affairs of the module. Now, after we reach 200 or 300 kilometers per apogee, the space shuttle will now have to rely on its OMS system. The OMS system stands for Orbital Maneuvering System. Orbital Maneuvering System runs on monomethyl hydrogen. It also runs on nitrogen tetroxide for oxidizer, and it's responsible for circularizing the spacecraft. Now, what I mean by circularizing, I mean the point where the apoapsis and periapsis are about the same. This is what circularization is. Sometimes the orbit can reach about 100 kilometers of difference between the periapsis and apoapsis, but that's highly unlikely. And the only time that you would need to circularize an aircraft like this is when you need a ferry flight. For example, most of the flights that the space shuttle took were ferry flights that were carrying payload back and forth. But for some flights, they just abandoned things in space and left them there. There were a few disasters because of poor OMS maneuvering. We know the Challenger disaster, which is quite unfortunate. But it was all due to the fact that the solid rocket boosters ignited and part of the O-rings were damaged, which led to catastrophic engine failures, systems failures. We lost most of it. Or the entire crew was unfortunately lost. But the solid rocket booster systems that I mentioned before, the same systems that are responsible for driving solid rocket boosters away from the main shuttle pod and the main external tank, were used to drive it away from any civilian population, because the solid rocket boosters are essentially giant missiles. They can be used for all sorts of malicious reasons. These are the OMS motors. They're very weak, in fact. But it doesn't matter that they're weak, because there's no air resistance that will stop them. They can essentially fly without any external control. They're only ignited about 2 times during the entire operation. One is during circularization, and one is during deorbit. Once the aircraft has started deorbiting, well, then we won't need to use the OMS anymore, because gravity and air resistance will do the rest. This is where most of the flying will be done inside of the space shuttle. The commander and sub-commander of the space shuttle do not have the traditional responsibilities that any other airline captain or a traditional aircraft captain would have. Instead, they're just responsible for maintaining the status quo. The status quo is essentially all systems are already go and all systems are already working, and sub-commander and commander must be responsible to keep that as it is. Mission control and doing most of the work. This is the space lab. This is one payload that the space shuttle took with it into orbit. It was attached to the space station and then it was brought back down. The space lab is still operative. It had a few issues where it was discontinued, but the space lab was one of the principal payloads of the spacecraft, and also made the pressurized area of the spacecraft higher for us to venture in. So, for example, if this is the traditional area of the spacecraft, and this is the pressurized area of the spacecraft, this area would be completely uninhabitable. There'll be radiation, possibly solar damage. There's no oxidizer, there's no pressurization and oxidizer out there. But when the space lab was attached to it, it carried its own oxidizer, it carried its own life support, and then it could sustain an additional 1 or 2 astronauts. So this is when the space lab was operative, the space shuttle was at its maximum pressure capacity. Pressure capacity is when an aircraft or a spacecraft, especially aircraft at higher altitudes, can operate in a way that's survivable for the crew. Now, before I proceed, does anyone have any questions regarding this? This is the point where the spacecraft will dock with the ISS. This is quite a complex maneuver, so I'll explain how that works. If this is our current orbit, 300 kilometers, and the ISS, which does orbit quite high, is orbiting at 400 kilometers. Then, to get to a higher orbit, the spacecraft will perform a Holman maneuver. It was named after a German scientist named Holman. He did a lot of work in orbital mechanics. He did not invent the Holman transfer, but he likely coined the name for it. Essentially works well. Everything in space will be relevant based on your velocity. Your velocity squared, or simply your velocity, will be responsible for the height of your orbit. If your velocity gets too slow by air resistance, debris, internal issues, or anything like that, your orbit will rapidly decrease, and then you'll have a very low periapsis, and that's going to be a disaster. This is the same system I mentioned before. Now, this is especially relevant for the second transfer because it means that once we have completed the first burn, which is the first part of the Holman transfer, we can say that this is burn number one. Let's pretend that this was 300 kilometers, and this, for example, is 400 kilometers. Our apoapsis after this burn, because our velocity is increased, will now be something like 400, 390, 380 kilometers. Why is this important? Well, once we get to 400 kilometers, we will easily miss the ISS, which is the body we're supposed to be docking with, if, for example, our apoapsis is 300 kilometers. So we'll be able to temporarily catch up with the ISS, but we'll quickly lose it afterwards. So that's why the Holman transfer is a process of two burns. The first burn is to get up to the apoapsis of your target body. The ISS travels at an altitude of 300 kilometers. Once we've reached that point, the second burn will also raise our periapsis to 300 kilometers. So it's circularized. Once both the periapsis and apoapsis are circularized, matched, and are aligned with our target body, that is when we can say that we have docked. Now, as for the process of docking, such as spacecraft. Our velocity squared, I can also explain it. Because this is squared, this will be. So essentially R is our current altitude. If the space shuttle is flying at 250 kilometers, that's our current altitude. So we can divide that by 200, we can substitute that for 250. And one. And this is the final equation for velocity. Once we have completed this, the space shuttle, the space station will be only a matter of kilometers away, and at this point, mission control, as well as the astronauts currently inhabiting the ISS, will help to guide the two craft together. This happens through a process known as docking, and at this point, thrusters like the OMS will be completely irrelevant. The OMS thrusters, which you can see here, these are OMS thrusters, they'll be completely irrelevant, they'll be of no use, and we need to use a system called the RCS thrusters, and we also need to use, I'll show you. And we also need to use a system known as the reaction wheel system. The reaction wheel system is a control system. This is not found on any aircraft that we know of on Earth, but it's quite a sophisticated system with two rotating discs, like this, at the center, essentially giant centrifuges, which are used to change the center of mass of an aircraft, so that once the center of mass changes, its inclination, attitude, pitch, direction, and possibly even velocity will change with it. This is useful in space because there is no air resistance. We cannot fly the aircraft using air resistance. If we use the ailerons, which the spatial definitely does have ailerons, it definitely does have a rudder, it definitely does have an elevator system, but without these we cannot use any of these in space. So we need to use the RCS. The RCS thrusters. You can see part of the RCS thrusters here. This is on a different spacecraft. This is part of the NASA program, known as the Atlas and the Orion spacecraft. But they use the same concept. These RCS thrusters are small monopropellant thrusters. They can't cause any major flight control changes. However, what they're good at doing is small attitude changes. On a traditional aircraft, this will be done by the ailerons, elevators, the rudder, and possibly even an engine. You all know about what happened to United Airlines Flight 232? There was the explosion in engine 3. It was an MD-11. The MD-11 lost its engine 3 or 2, depending on how you look at it. It lost engine 3, and the explosion caused damage to almost all the flight controls. They lost complete flight controls, and they had to fly using engines because there's no air resistance. You cannot fly using the rudder, the elevators, the ailerons. These are all useless. So they had to manage by turning off engine 1 if they wanted to bank right, and then if they used engine 2, they would use that to bank left. That was the only control they had. In space, we cannot. United Airlines Flight 232 unfortunately did crash. That was because the flight control was that bad. In space, NASA engineers didn't want to make the same mistake that the crew or the people that were responsible for United Airlines Flight 232 made. They implemented this system so that even with complete loss of rudder, aileron, and elevators, the spacecraft could still be very safely steered into a direction like the ISS. This is known as the aft RCS. It's at the very back. It's responsible for small attitude changes. If the RCS thrusters are completely depleted, then OMS thrusters could possibly be gimbaled back and forth, because they also run on monomethyl hydrazine. And the OMS thrusters are also very wide, which means that they will work very well in a vacuum, although they are typically used for lower orbits, essentially. However, the RCS. Also, a big good copy now. The RCS are designed for constant adjustments. So the RCS engines could be fired on and off multiple times a minute. So you could fire an RCS engine about 50 times on and off per minute, and it will hopefully not be damaged. If you did that to any other typical rocket engine, like a liquid fuel rocket engine with hydrogen and oxygen per se, the rocket engine would likely collapse. It would fail. You'd have possibly fuel leaks. You could have a termination of thrust. On a small monopropellant thruster like this, they're essentially designed to be damaged. They can be damaged and they can also be flown up. Right here in this Columbia or Discovery, I believe, whatever the space shuttle is, it's designed to slowly run towards this docking port here. The docking port is actually quite a genius design itself. It uses pressurization mechanisms so that once an astronaut or payload is brought through the docking bay or the airlock, the air will be completely contained inside itself. If the RCS thrusters fail during the docking procedure, then one of the bolts that are designed to secure the airlocks in position could have failed, and that would cause a massive pressurization. The astronauts could potentially be sucked out of the ISS and the space shuttle. So this is why RCS thrusters are arguably the most important engine of this entire spacecraft. Once it is docked with the ISS, the space shuttle will typically exchange all sorts of fuel, back and forth, hydrogen, oxygen, life support, food, water, supplies, all these things. In fact, water is important for the spatial missions in more than one, because even prior to launch, water is sprayed on the launch pad. So that the sound that the space shuttle makes during launch will not be dispersed throughout the entire civilian population. If this sound is dispersed, it could possibly even cause deafness. The people watching, who are at least within a 20 to 10 kilometer vicinity of the space shuttle, they could go completely deaf if the sound is not dispersed. That is why the water is sprayed on the launch pad, and there are essentially two giant struts which are extended, and then the thrust will be headed out in those two directions. Once it has reached the ISS, and they decide that it's time to go back home, it's a very calculated maneuver of balancing the space shuttle's typical flying characteristics, which is that of the glider. But as you can see, the space shuttle is not a very aerodynamic aircraft. It can fly, theoretically speaking, but astronauts and test pilots who flew the space shuttle often described it as a flying brick. And they said that the space shuttle is not really flying, but it's falling in a controlled manner. So, if we go back to this here, you can see that I before I talked about the two valves on the bottom of the space shuttle, on the heat shield. The heat shield is actually made out of ceramic tiles. These ceramic tiles are responsible for absorbing most of the heat that comes during re-entry. Remember that, even, you know about the supersonic aircraft that we use on Earth? These supersonic aircraft, they could reach extremely high temperatures. This was an extremely dangerous procedure to do. But the space shuttle is not flying at supersonic speed, but it's flying at hypersonic speed. If some of the heat was distributed wrong, this could result in a total extermination of, essentially, the contents inside. Extremely valuable contents, like the humans that inhabit it. This is why it's important to make sure that the heat shield is accurate, it depletes properly, it ablates away properly, and that it also can be reused. Now, there is one example of the disaster that happened during re-entry in a space shuttle. The space shuttle heat shield did not distribute the heat properly. It overheated. It was an absolute tragic event. The remains could be seen all over the United States. And in order to prevent that from happening again, NASA was actually cutting corners. They were being extremely cheap with the heat shield. They had about 50 heat shields per one side, and then the other was basically a giant blanket. It was a blanket of ceramic tiles, but it was not made with the same precision with the ones on the outside one, because they assumed, in order to cut costs, manufacturing costs, that if we have enough heat shields on the outside, then most of the heat would naturally go towards the outside. That's not what happened, and the heat grew to an extent that was unbearable. And after periapsis, this slow re-entry to Earth's atmosphere, there was a loss of communication. They first assumed that this is a communication glitch, but it turns out that the space shuttle was completely gone. This was not the only disaster. There was also the tragic disaster when the space shuttle was trying to go into the ascending position. The SRBs had not even been separated yet. Yet the problem with these solid rocket boosters, it's O-rings, and frankly enough, it was more construction costs that were cut. The O-rings failed, it melted. You know, the famous Richard Feynman experiment where he held up O-rings and said, this is what happens to O-rings when they reach too much height. They melt because they're not made out of the same materials that the rest of the space shuttle is. So unfortunately, we lost two space shuttles that were all due to very avoidable problems, but I'll show you how a very standard textbook procedure into descending it works out. First of all, we need to lower our velocity. We already had an example here of velocity squared. Now, our velocity, as you know in the rocket equation, now delta V, which is our change in velocity, our change in momentum, our change in speed, increases with our exhaust velocity, our mass, and the pressure inside of the rocket. The exhaust velocity is how much velocity a rocket engine can expel at once. The pressure inside of the rocket is how much pressure the rocket will take in the nozzle in order to create ignition, in order to create thrust, in order to create energy. In a jet engine, this is achieved by using the existing air of our atmosphere and then sucking it in, but the rocket does not have that limit, so it needs to use its own oxidizer. If we produce delta V, for say, in 100 meters per second, in the retrograde direction. The retrograde direction is the direction opposite to the orbiting body. We live in in terms of spacecraft, our country is quite blessed. We live on the equator, there's plenty of natural momentum, we also have very low gravity compared to other countries. Because of this, our country naturally rests in the prograde direction. Once a spacecraft does take off, like for example like this is in the prograde direction. If we go at 500 meters per second, or even like 40 kilometers per second, which some craft did indeed reach 40 kilometers per second, in the prograde direction, then our orbit will generally increase until we reach escape velocity. Escape velocity is the velocity that is needed to escape the Earth's gravity. It's extremely hard, but once we can do it, it means that essentially we'll go into somewhere in the space station, the solar system, and start orbiting the sun, which is the nearest gravitational body. If we burn retrograde, however, it means that our orbit will not increase, but it will decrease. If we can decrease our orbit, it means that we can go into a part of the atmosphere like 100 kilometers. It's legal start of space, 100 kilometers. 80 kilometers is still very much on Earth. 70 kilometers, 60 kilometers, 50 kilometers, even some planes can do this, right? So if we can get into a point of the atmosphere that has a lot of air resistance, then there is no engine power needed. We can rely on gravity and the natural air resistance to slowly glide out of spacecraft to the ground. This procedure this is the heat shield. When NASA's first, at least the United States government, they were the first people in the USA to start experimenting with heat shields. They decided that the best way is to make sure that the astronauts do not absorb most of the heat, but the craft does. I'll explain how that works in a minute. If we have a craft like this, for example, what's going to happen if we add too much pressure to this? It's going to overheat. Well, it turns out that this is actually not what happens. NASA engineers, because they were used to classical mechanics, they were used to Newtonian physics, and this is quite predictable when working on a very controlled environment on the Earth. However, the first NASA missions into outer space revealed that once you send a rocket at like hypersonic speeds into the Earth's atmosphere, the heating is not going to be from friction. It's not going to be from air resistance, but rather the air molecules that the spacecraft is flying into cannot adjust quickly enough. Once it cannot adjust quickly enough, it's going to form a bubble, and this bubble is going to conserve all of the heat within it, and this is going to cause the overheating, not the friction. Friction accounts for about 20% of the heating, but most of the heating is actually because of the air bubbles that this produces. So this is the area that they wanted to concentrate most of their energy on, most of their power on, most of their manufacturing costs on, was ascent, because otherwise you could have no overheating. The Russians, you all know about Leica and the story of what happened with her. The Russians tried to do this experimentally. They physically sent multiple spacecraft out, and some of them did not make it back, and they decided that we could use one of these. NASA decided to do this in a simulation. They had 5 different modules using different heat shield characteristics. They're all ceramic tiles. They decided that for an object as large as this, I mean, at the time, this was the most complicated flying machine that NASA had ever known, or the United States government had never known. And it was so complicated that they were wondering if, because of the mass and the weight of this aircraft, if we do actually send it into the atmosphere, then at least parts of it are going to be absorbed by the astronauts, because they have to also absorb the G-forces that are associated with this. In actuality, the space shuttle can only absorb about 3 Gs, so 3 times the acceleration due to gravity. If it goes any higher than that, then it will disintegrate, and we'll lose it again, like in Challenger and Discovery, in Columbia, which is why we added this type of heat shield. This heat shield is designed to solely ablate away. So we have an ablative layer. This was not known at the time when NASA first discovered these heat shields. You have a first layer like this here. This layer ablates away for the first 90 seconds of the re-entry into orbit, and then once this layer is completely melted, it's not used again. It's not reusable, but it does work. Once this second layer is also used, it means that about 20% of that will be used. Once 20% is used, this final layer will not melt at all. It will completely absorb the heat. There will be multiple cooling systems in the space shuttle to make sure that the electronic systems are safe, secure, sound, and they're also working. If this does not happen, we'll have another Challenger or another Discovery or another Columbia. Which is why, once they have reached Earth's atmosphere, they were presented with another problem. There was no GPS at this time, and the space shuttle could not carry all the sophisticated navigation systems that traditional aircraft had the liberty of carrying. They had the luxury of carrying complicated aircraft systems. They had They had a sophisticated network of VORs, air traffic control systems. The spatial had none of this when it was first being produced into service in the 1970s. The GPS is not even invented yet. They had to run calculation, but they had to rely on the Doppler shift. Ground trackers in NASA, Kennedy Space Center in California, could track the position of the space shuttle, and by looking at the light reflected on the space shuttle, and utilizing the Doppler shift and the Doppler effect, you could calculate the altitude. And with this equation, once you have the altitude, which is r, and you also have the periapsis and apoapsis, it's very easy to calculate your exact position based on your velocity. This was a revelation, and NASA used it to slowly guide these early space shuttles to the ground, and here came the final point of the landing, which was flying it like a giant glider. I'll show this one. We are at this stage now. We've re-entered. We've done our orbital tasks. We've entered into orbit. We've dropped all the external fuel tanks. They could even spend several months, weeks in space, which is why after this flight, the astronauts are also experiencing what's known as space nostalgia. They've been very accustomed to weightlessness, the constant feeling of free fall. Once they are slowly ascending into about 70,000, 60,000, 50,000 feet, which is and 40,000 feet, which is the standard height of commercial airliners, they're starting to feel their first taste of gravity again, which is quite disorientating, especially because they've been in free fall. For this, NASA designed a system in order to not flex the astronauts so much. They'll come in at an extremely steep angle. There are some airports in this world that are known for being extremely steep. London City, some airports in Hong Kong, these are known for being extremely steep, in terms of the glide slope. For the space shuttle, if this was its orbit, this would be its glide slope. In fact, its descent rate was close to the terminal velocity of standard aircraft on Earth. The terminal velocity is the speed at which you fall, and then you cannot go any further than that. That was the vertical speed of the spacecraft that it was traveling at, and it was designed to not trouble the astronauts by sudden amounts of gravity and loss of weightlessness. Once it had been completely guided down to the runway, you can see that it will go past through about 5,000 to 4,000, 3,000, 2,000 feet, and then in combination with mission control, they'll clear the Air Force Base, and then the space shuttle will be able to land after a very long journey. At this point, the space shuttle would likely need to be repaired because the heat shield needs to be completely replaced. About 50% of the heat shield, so 50% to 90% of the heat shield will be completely inflated away, will be completely damaged. And this is why the space shuttle was so unique in this regard, because heat shield was able to withstand so much pressure. And now this is extremely important because I think there are some things in the space shuttle that can be utilized in the traditional mainstream aviation world. The space shuttle is able to fly even when it has no thrusters, as in it's able to control itself without any thrusters. The tragic accidents such as United Airlines Flight 232 with the MD-11 would have been completely avoided if traditional aircraft also had a better reaction control system with small thrusters and also better reaction wheels. There are some attempts at adding reaction wheels to an aircraft. There is, in fact, the Dream Chaser, which is a small orbital spacecraft, but there have been no mainstream major attempts in order to blend this space technology with aircraft technology. I mean, a lot of mainstream aviation technology did indeed come from NASA's funding for the space program, but it takes a while for it to be tested, used, and eventually come into production. So, I hope I've done a good job of explaining the parts of a space flight, especially the space shuttle. And I also did try explaining how the horrible accidents, such as United Airlines Flight 232, could have been avoided by copying some of the technology that NASA put into its space shuttle program. I don't know if I have much time left, but I could go on.
Yeah.
First time?
Yeah.
Okay. Well, what happened on United Airlines 232 was it tried to regain control by using one engine after the other. It failed. That was mostly because the elevator systems were so damaged and the aileron systems were so damaged that the complete hydraulic system involved the space of the aircraft was lost. They could not control anything. If this happened to something like the space shuttle during landing, during descent, if they lost complete hydraulic control, they could rely on the RCS. They could rely on its ammonium process. They could rely on the small gimbals. They could rely on the reaction wheels. it does not always have to solely rely on the ailerons and thrusters and the traditional thrusters that doesn't need use. It's a giant glider, after all. So I think the space shuttle is quite an important point of connection between the aerospace world and the traditional aviation world. Thank you.
Megha, any questions?
Do you have any questions?
Yes, you may ask.
Yeah.
I think biggest question is you are not able to follow him due to his accent, right? Is that?
සිංහලෙන් මොනවා හරි අහන්න ඕන නම් අහන්න.
Yes. He's
සිංහල හොඳට පුළුවන්.
You can ask him.
Explain about doing signal and special day.
මේක නම් ප්‍රශ්නේ ලාවනා කරන්න අපිට
Yeah, you may ask anything.
In terminal velocity, does it come like head down or just have to?
No, it has a very steep rate of descent until about 1,000 feet. At 1,000 feet, it will start leveling off. But until 1,000 feet, it will be at constant terminal velocity, which is, I mean, no other aircraft does that apart from the space shuttle. And that was mainly because they wanted to not, they wanted to slowly introduce the effects of gravity to the astronauts. So they took that terminal velocity over this time, and that was that.
Excuse me.